Hi everyone. We should be coming live to you from beautiful Lisbon, Portugal. Um, so if there is any problem, please let me know, uh, and we'll fix that technical issue. Other than that, very nice to see you and have you there. We are gonna talk about a very important release that's gonna happen soon, and that has to do with PyMC, of course, PyMC 3. That's the package you all know and love to do Bayesian statistics. And we'll talk in particular about V3, V4, sorry. So the coming very new version. And to do that today, we have a very special guest, Ricardo Vieira, which is here with us at the PyMC Labs retreat. And without further ado, I will introduce him right now. So, Ricardo, welcome to the live stream.
Hello, Alex.
Yeah, thanks for taking the time. I know you are the local guide here at the PyMC Labs retreat, so it's great. It's great to have you with us. But you're not gonna talk about the Lisbon landscape and Portuguese food and so on, right? That could be another episode. But today we are gonna talk about V4. But first, as usual on the podcast, can you tell us a bit about you? So, what's your background? Like, how did you come into the stats world? What's your story, basically?
All right. Thanks, Alex. So I am Portuguese by nature. I did. I started in psychology, and then moved to neuroscience, and step by step, I got more and more into technical data analysis and Bayesian stats eventually. And then I found the PyMC 3 library, and it was just great community and a great library to work. I started contributing, and here we are, all working on this library here in Portugal for a couple of weeks.
Yeah. So thanks for this introduction. And how did you go into the patient stats actually? Like, because now we know you do
Yeah.
brain stuff and neuroscience and mathematical stuff, but like, how did you end up contributing to PyMC, and before that, how were you introduced to patient stats?
Right. So I started with classical frequentist analysis.
Yeah, we all did.
Exactly. It was fun. You could find the 20 variations. And after that, I felt like maybe something more would be also nice. And I think Bayesian stats just shows up if you look a bit further and you want to keep challenging yourself.
Yeah.
And the library was Python was the language I was used to. So it was, I think, natural. If you like Bayesian stats, you like Python, you land in PyMC3, right? And from there, it was, started sharing a bit, improving some of the notebooks we have in PyMC examples, fixing very simple bugs, and you get addicted very quickly.
Yeah. Yeah, that's true. And so when was that? Like about a year ago, something like that?
Yeah, so I joined. I was invited by you. I think
Yeah,
you are
yeah,
the one
yeah. Indeed, you owe me eternal respect for that. I
who
think.
sent a letter with a stamp. I think, yeah, exactly. Beginning of the year. So January, end of December.
Okay.
So then I joined the core.
Yeah. Okay. And now you're working with us at PyMC Labs. It's great to have you here. Um, not only to have you as a local guide. Um, so what we'll do now is you'll go through. You have some slides, right, prepared for us. So what we'll do is let you go through the slides. You'll basically tell us a bit about V4, what's under the hood, what we have prepared for the coming release. and also a nice other project that came out of that development, but I'm not gonna spoil your being and game here. So I will now share my screen and let the world discover about what you have to tell us.
Exactly. So people can follow this link if they want to see the slides on their own pace. We can start.
Okay.
Yes, so we'll talk about PyMC3 v4, not to be confused with PyMC 4. It's just going to be a major release of PyMC3. Some things are going to change, mostly in the backend. So we're going to have a lot of new functionality and a lot of new flexibility, and also less bugs. And hopefully users will not have to change much in their code, only to make use of the new super cool features that the team has been working maybe now a year and a half focusing on v4. So let's see what's new. So biggest change is we are using Aesara backend. Originally we had the Tiano backend. The library it's not being maintained anymore, and we had this temporary fork, this Tiano PyMC, that we just maintain now for v3. But for v4 we have a fully owned Aesara backend that we are improving, not only for PyMC3 but as a general Symbolic library, and that's where most of the new features are actually going to come from in v4.
Yeah, so Aesara is basically a new
both library and the reason for the name.
Yeah, daughter of
the mythological daughter.
Yeah.
Yeah. So the big change is we now have this new Aesara operator. The same way we have addition and subtraction, now we have random variables, which allows us to work with both random number generators and distributions, basically as a first-class citizen in a library. And this will be, and this is really the core of the new functionality. It comes from these operators, and we'll show a bit of them, how they work later on. So also Aesara was refactored a lot to make it very flexible in allowing you to compile not only to C code as Tiano did, but now we can also compile it to JAX and to number, and so we can make use of all the power of those libraries to have fast code that runs in the GPUs without us having to, necessarily the expertise to write code that's performant on those systems. And the library is now flexible enough that it's very easy to just write our graphs to basically any backend that we feel we could benefit from. Right, so they should get, if those libraries, if this kind of code runs faster in their machine or whatever system they have, they're not going to have to write JAX code, but they're going to be benefiting from JAX speed, for instance. So for users, nothing is going to change, only that they now can decide, let's try this not in C code, let's see if it goes faster in number.
Yeah.
Let's see if we can make use of the GPU by just compiling to JAX, because in my machine it runs well on GPU. So it's more flexibility without cost, and it also opens the door, maybe the next backend is not yet around us, and it'll be easy to just plug it in.
Yeah, I see.
Right, better shape handling. This falls from the random variable. So a lot of PyMC3 bugs and pain came from the fact that we were kind of plugging in distributions a bit artificially into Tiano models. And now, because we are using random variables, everything is going to work very well. We have all the functionality of shape inference and proper error messages just by using the random variables. So a lot of bugs and a lot of pain should go away. And there's already gone away, right? This is code we already have.
Yeah, I mean, better shape handling, I'm all for that. I think a lot of listeners and viewers will be happy to hear about that, especially automatic shape handling. That's just great. I did a few, like I played a bit around with the. So for people concretely, the master branch of PyMC now on GitHub is the version 4. So if you want to play around with that, you can go ahead and clone that and use the master branch. I did play around with that already a bit, especially to test the shape handling. That is especially comfortable and nice to have that now.
Yeah.
So yeah, well done on that. I mean, that's so great. Often a big portion of the time you spend while developing a model is shape handling, right? So I mean, if that's automatic, that's always much better.
And not only better shape handling, also more flexible shape handling. It will be easier now to have variables grow without having to rewrite the graph. So all nice things, for instance, that show up commonly in posterior predictive sampling, right? It's mostly about changing shapes of variables and putting values there. All these things are now much more easier to work with. Right. Next one would be we now have much faster prior and predictive sampling because, again, everything works with random variables. This is exactly what random variables do is they are the equivalent to NumPy random methods or the SciPy ones. So they are operators that draw samples, and just by using them, we get a lot of speed up when we do prior and posterior predictive sampling.
I see.
That's a great feature.
Yeah, it does sound great too.
Right. So there's also some experimental libraries that now we can use with PyMC3 that allow to have fully symbolic samplers. So not only our model log P evaluation and gradients are symbolic, but actually the nut sampler can be symbolic, and so we don't have this cost of going from Python to whatever backend our model is, and potentially we're going to have crazy speedups just because we can now avoid easily Python altogether, other than writing the code, which is the best scenario.
Yeah, I mean, yeah. Again, that does sound super nice to have that, especially if you can run all that in like not using Python there. Yeah.
Your sampler and your model to the GPU. We don't know yet what's going to come out of there, but now it's a possibility, and that's a quite exciting possibility. Right, and the one I'm mostly interested in or working more with is that now we have much more tools with which to specify flexible models or with which to work with existing models to make them better. For instance, Alex is the one controlling the slides.
I know I have a lot of power here.
Exactly. So we can do symbolic rewrites, right? We'll be able to very easily convert a centered model to a non-centered model without requiring you to change how you write the model. We might be, or we can easily also find, replace distributions by compound distributions when they have like conjugate posterior, right? And so a lot of symbolic features just now it's going to be easier to work because we have a fully symbolic model and not plugging these hacks that we were doing in PyMC3 out of necessity, right?
Yeah, so wait. So that means that basically, thanks to the symbolic infrastructure that we now have in V4, that is going to make this type of handling graphs and even reparametrizing models much easier and even automatic, right? So, for instance, one you mentioned that I'm sure listeners will be familiar with is like if you need to switch from a centered to an uncentered parameterization, now that should be much, not only much easier, but even a lot of the time automatic, which sounds amazing, right?
Exactly. So we're gonna have right. So we're gonna be able to have good defaults. You write a model that's easy to understand, and we now have the power to tweak it a bit, see if that sample is better. Obviously, we're not gonna take control away from people, but and they're also going to be able to iterate and try different things much faster, right? You don't need to go every line you have center parameterization and replace that manually, which I think everyone does who writes for long enough. So yes,
okay,
that's a great
awesome.
potential there. And this will be exactly what you're talking about. We'll be able to compute the log p of random models that are not necessarily just a distribution. So not just here you have a normal distribution, but maybe here you have a loop, or you have some clipping going on, and you're going to be able to ask, can I get a log p for this? So you're going to be much more flexible in the kind of models you can create, for which then we can compute log p's and sample as usual. And that's exactly what I'm going to show a bit today. And we can go there. So I'll jump a bit in how PyMC3 used to work, just to give a bit of context and maybe make it a bit more intuitive why we can do this and how actually we are going to do this. So here is a snippet of PyMC3 v3, and I'm just showing, creating a normal distribution and saving into X, and just checking what kind of object is returned, and it's this thing called PyMC3 model free random variable. Which under the hood is just a Tiano, used to be a Tiano tensor variable. Basically, it's a symbolic input, but it's something that lives a bit, let's say, in isolation. There's nothing else to it than just saying this is a kind of input. Actually, if you go one more slide, it's so we cannot ask, for instance, what variables are linked to this X, to this normal distribution, right? There's no owner, means this just lives completely isolated. And this is exactly what we were doing. We were plugging these random variable, not these symbolic variables when we call the distribution, but they didn't really work with the rest of graph. So if you do additions or if you do any deterministic transformation, we couldn't do much with that other than store it and plug it into other distributions. In V4, for comparison.
So that's new. That's the new part, right? Now we're going into the meat of the presentation.
This is where it gets exciting. So you can already use V4 if you install from GitHub directly. You're going to see a warning message mentioning this is still experimental. And so if we run just the same code, we call PM normal, nothing changed in the basic interface. Well, we have some nice pretty printing that was added recently, but now if you ask what type of, if you ask what type of variable, it's going to be it's going to be the same type of variable, but, the output is the same type of variable, but we are now working with random variables, which we'll see in the next slide. Right, so we import Aesara here just to do a debug print. So if we do dprint on X, we can see, we are not just working with an empty tensor. We are working with a random variable that has a bit of, a lot of going on, let's say. I can just show. So these 5 lines are the inputs into a random variable in Aesara. The first one is always a shared variable that represents the random state. The second one is the size of the variable. In this case, we didn't define any size. We just call PM normal, so it's just the empty list. Third one is just the type of variable. It's a numerical code that, it's going to be different if you have float 32 or float 64 or integer. And then are the ones that we care about. So we have 0 and 1, which is the default mean and standard deviation. So we know that now we are working, this X is a unit normal distribution. And this little thing is going to give us a lot of power, as we'll see soon.
And so just to add to that, yeah, that's super useful exactly to debug your models. Like when you work on that, like as Ricardo explained, you will always have the same structure when you debug print a random variable. So that's a good way for you to go into debugging your models. That's something really useful. That wasn't like, at least here the user experiences is improved compared to V3. So I mean, this is super interesting to have that.
Right, and if you forget what your X is, now you can see, right? Before you would have the name of the distribution and not much more. So yeah, we have now, yeah, fully random variables. They work as a random variable. Once you get used to it, you'll see you wouldn't want to go back for sure.
So next.
Right, and the cool thing, as we said, these are random variables. We can generate random numbers. So if you call eval on a random variable created by PyMC3, you're going to get random draws, as if you call numpy.random.normal.
Yeah, this is super cool. I used that when I tried V4. And yeah, that's great, because before in PyMC3 or in V3, you had to use .tag.testValue or .tag.testValue.shape, whereas here you can just do x.eval or x.shape.eval, and you'll get what you want. So the access is much more direct, let's say.
Yeah.
So next one.
Yeah, let's go. So now let's have a bit look at the internals, what we are doing with these random variables. How do we make them, PyMC3 objects that allow us to do all the cool PyMC3 stuff. So when we called before pm.normal, what was happening under the hood is we were creating this Aesara random variable, which you can do by just calling random.normal in the tensor library. And then we have this helper function internally that just registers the random variable to the model and gives it a name. And then what you'll see is the model now in the free random variables list includes our X. And we also have a dictionary that maps random variable to a value variable. And the value variable was our previous X in V3. The value variable will be the input to the log P, will be the thing that our sampler is going to work with. So we have this very clean map between the original model and what kind of inputs are replaced when you compute log P. But if we want to work in the random side or in the symbolic side, we can do everything still with the original random variable.
Yeah. Now, what about .dist, Ricardo? I know that everyone
.dist.
Everyone is wondering about .dist. Okay, you can see that on the chat. So what about that?
Exactly. So .dist, I don't know if many people worked with it. .dist was a way of saying I want a random, basically I want a normal variable, but I don't want it to be just something direct in the model that I want to sample. So one place where used was, for instance, if you wanted to create a mixture of normal components, you use the .dist, which is it's going to be, I'm going to use something normal, but this is not a variable in the model. Right? And .dist is going to work here similarly. We're going to say, maybe I want something that starts from a normal distribution, but this is not the thing I want yet. So we still have that ability by calling .dist. .dist behind the scenes is just returning, in this case, it's just returning what we had before, is just returning this Aesara random and normal. Also, there's other things, for instance, in many distributions in PyMC3 can be parameterized differently. You can give sigma or tau instead, if you want to define it in terms of precision. And the .dist takes care of converting one to the other before returning let's say, the canonical random variable. So we can see here, this code has exactly the same effect as before. We still get an X that's a normal variable that you can debug print. The same way, you can still call eval to get a random draw. Yes, so how do we get from this random graph, how do we get a log P, which we need for, some of the things we do in PyMC3. So the way we are doing this is for different kinds of random variables, we're just saying if you have a normal, this would be the log p expression. And for so before you used to call, you could call pm.normal.log p. That you cannot do anymore. What you can do is just call pm log p and say, I pass this random variable. You also need to pass the new input, right? This value variable that we create behind the scenes, and you get the same kind of expression back. So in this code, I'm showing this. So we are creating, just normal pm normal x is going to return this Aesara random variable, which we can evaluate symbolically. Behind the scenes, we also created this mapping in the RFEs to values, where you pass the random variable and you get the respective value variable. And then we can call pm log p for this random variable with this value variable, and then we get this x log p that we can evaluate as our function, so we can get the log p at 0, and we get the right result back. Right. One more. So going back, going really deep and seeing everything that's happening behind the curtain. In this, so we can also create a value variable directly. We don't need to create in a PyMC3 model and then use the mapping to get it. And a simple way is just saying, create a random variable xrv, and the value is just going to have this. It's just going to be a symbolic tensor with the same type as the random variable, and that's enough. And then you can call the pm log p, and you can work the same way.
I see. That's a bit more. That's a bit more of an advanced usage, but that's interesting to have that in there, especially for people, for instance, who want to come in and join the effort on GitHub. But now let's go to the next slide.
Right. And the reason I mentioned is I will show some examples of the magic we can do now, and it's good to have an idea of these random variables. So, but at this point in our GitHub main branch, basically we can do everything that V3 used to do, minus some tiny corners with random variables. So in some cases faster for the predictive and posterior sampling, and with way less shape bugs. So I don't think we had a shape bug in the last 6 months that comes from V4.
Wow, that's definitely a performance.
Yeah. And now the question is, we got here. Now, what else can we do this? What can we push? The frontier of the library. And let's go. And what we would like to do is, okay, let's go beyond basic distributions. Let's ask, can we have models that do something with, using basic distributions as building blocks, but more interesting kind of models? One not very interesting, but already something we cannot do in V3 is, if we have, let's say we have a normal distribution and we just want to offset it by, let's say, a symbolic number, or in this case, a constant, or maybe another distribution. Can we ask the log p of these? Can we have a model that runs on, basically a deterministic, right, normal distribution with an offset? And the question is this. The answer will be yes, but there will, in theory, we can just call, behind the scenes, we can just call normal log p and just subtract 1 to the value variable, and that will do exactly the same. Yeah. And we can do this. I actually started some time ago a PR in PyMC3 to implement this kind of feature. So this snippet that has a bit of things going on. We have a log location variable that follows a normal distribution. We have a scale that follows a half normal. And then we have this x, which will be a unit normal distribution with the location shift and the scaling. And the question is, can we just now work on x directly? We could. We can see here that it worked fine. We could call the log p, and it worked. We got the right results as if we had the normal distribution with the location and the scale. But right? So things are not always so nice in in Python world. And one area where we easily find problems is when we have when we started working with different shapes and different sizes. Because now we, for instance, in this example, what I think is going on is we're creating a scalar, the half normal scale as a size of 2. And we are basically multiplying this by a size 1 or no size normal distribution, which should be very similar to what we had before. But now, the symbolic graph, the graph that's generated has basically a broadcasting, right? Which we can see if you go just one more slide. We have this dim shuffle in the graph, and now it's not so easy to say, what is the log p of the dim shuffle of, this multiplication, whereas before it would be very easy to look at the graph, we're just multiplying a base random variable by another variable.
So dim shuffle, can you just define that super quickly for listeners?
Shuffle is basically any kind of broadcasting that happens in Aesara is working with the dim shuffle operator. So when we expand something because of index or because you are multiplying two things with different shape, you're going to end up with the dim shuffle there. That is what telling, when we do this operation, the output is going to have this specific shape. So this is where we branched off. So we branch off to a library that's focused all on, working with this kind of problem and, being very flexible to generate log p's for arbitrary Aesara graphs. We are calling it APPL. And there's a bit of a wordplay here that which comes from, we are using the AE for Aesara. We have a few libraries that are focused on different parts of probabilistic sampling, and this one is just a wordplay, and we pronounce it APPL. And I have here a fake logo because we didn't know how to pronounce it, and we used to call it Apple. And for this presentation, it stayed with this temporary logo of an apple.
Yeah, so this is the new spin-off project that came out of all that development work on V4 and that Ricardo just talked about. Out of all that, it became necessary to come up with that spin-off project that can do a lot of things and that Ricardo will now show you. So let's go into that.
Right, so this is the example from the README. If you go to the GitHub of the APPL library, and the way we work is you generate a graph just based on using directly these Aesara random variables, and then we have this magical function called joint log prob, where you pass the random variables, you pass the value variables that we already discussed, and it's going to give you back a graph that represents the joint log probability of these variables. And the idea is that we're going to be able to pass a lot of interesting stuff and get back, correct log p expressions that will be able to then just plug in PyMC3. The way it works exactly is this: we have these two kind of inputs. This is the output, but the next slide, once Alex is free, we're gonna do some of the things that avoid that dim shuffle problem. We're gonna massage the graphs we have so that they are easier to work with and they are easier to pattern matching and say, okay, this corresponds to a location shift variable, or this corresponds to something else. I'll show some examples.
Yeah.
So this we are showing here is we have this database of rewrites that we apply that make graphs much easier to work with. So you put a dim shuffle. You can put a dim shuffle in other places that still they don't change the output of your graph, so it's still the same kind of graph, but now it's much easier to parse. We have stuff for working with indexing, stuff for working with broadcasting directly, dim shuffle, stuff like this. And this really gives us a lot of power that in PyMC3 would be difficult, mostly because in PyMC3 we work a bit step by step, right? You say here is the x, here is what depends on x, here is the likelihood that depends on the other two variables. And here, the way we are doing it is we can pass the entire graph and then we can reason about it holistically, which allows us to, make better guesses about what kind of log probe this represents.
Yeah, and so I'm wondering, would that be related? Would that be how you would do a rewrite of a model that's centered to a non-centered parameterization?
Yeah, for instance, yes, so you can pass the model with the variables and then you can say, don't just give me the traditional log probe, but apply this extra rewrite, let's say add it to this database.
Okay.
And this rewrite can look for variables and that can be reparameterized and do that.
Okay.
Right? So here we have the flexibility of saying what do we want to, what kind of rewrites we want to apply or turn them off if we don't want them.
Yeah.
Again, it will be able to basically apply all the rewrites by order.
Yeah. It can be automatic, it is automatic rewrites, but of course the user has the control over whether it wants a certain rewrite to happen or not, right?
Yeah, of course. And one of the rewrites we have already is for the transformations of variables, right? In this framework, it works as just an extra rewrite. Now I want you to transform, variables from a constraint space to unconstrained space. Add this rewrite.
Yeah, and we're gonna go into which kind of things you can already do with that.
Exactly. So yeah, I'm just going to show some examples now. It's more of a demonstration of, I think it really demonstrates the power of this approach. And I think it will also excite people because they'll be able to make use of this in PyMC v4. And my implicit motto in this library is if you can generate random draws from your model, then we should be able to say, this is the equivalent log probe for this kind of model. So one thing, one of them is monotonic transformations. So in this, which our example was before, the location and the scaling of variables. So if you create a generative graph that has some base distribution and you shift it and you scale it, now we can also generate the log probe for this. So this is how the code would look like. So we are creating this scalar B. We have a base random variable that's just a random normal. I actually have one more step here. We scale the base random variable and we exponentiate it. You could imagine this is something you do in a deterministic because this is this is what you want to use as input to another distribution. But now we can have the log p be defined in terms of this exponentiated scaled variable. The way you do it is just essential. You just call joint log probe. You say, this is my random variable. This is my value variable. Give me the log p. In this case, we are compiling it to Aesara function instead of calling .eval, which is how you should do if you are not just debugging. And we give some, so this is actually from our test library. And in this case, maybe some readers will have noticed the log p of this graph is exactly the same as a log normal distribution. And we can see that the evaluations work out. Another example is just, you have some random variable and you clip it. Let's say whatever value is smaller than -1 or bigger than 1 becomes equal to the edges, which might sound strange, but might also sound familiar. And we can ask, what is the log probe of this? And
that would be, so that would appear in my, is it censored data?
Right, data that above cutoff, all the values are going to be set to that cutoff.
Yeah, so that's censored data in comparison to another kind.
Truncated data.
Okay, truncated, exactly.
So exactly. So now we can have censored variables for any distribution by just asking what is the log probe of a graph that's where you are clipping a random variable. Right. So if you generate samples with these, you're going to get the clipped samples, and we can also ask the log probe. we can do a lot of funny mixtures just by playing with indexes, right? Which is mixtures. If you are generating random draws, you are usually using index, right?
Yeah.
You say, take a Bernoulli random draw. If it's 0, go from this component. If it's 1, take from the other component. And similar here, if you generate a graph that represents a mixture, you can get a log prob that represents the log prob of a mixture.
Okay, yeah, I see. And just so to be clear with listeners, so the cases you are showing here, like, are those new features that, like, these are new things that you now can do with V4 that you couldn't do with V3, or was it possible with V3 but very complicated to implement?
Yeah, so with V3, for instance, you didn't have censored, with V3, you didn't have censored variables. You could write your own custom log P, but now, I mean, you can, it's going to be very easy for us in the PyMC library to generate censored distributions for any kind of distribution, because behind the scenes, the only thing we need to do is get a base distribution, clip it, and ask here APPL, just ask us what is the log probability of this kind of variable, right? And we won't have to do, create a version of a censored variable for all kinds of distributions. We're going to have for all of them immediately, as long as we have, in the case of censored variables, the log CDF.
Yeah.
Right.
Okay. Yeah, makes sense. So next case.
Right. So this is a big one.
So this has Brendan Willard written all over it, right?
So Brandon was, he was the one that's branched off this library, and a lot of ideas come from work that he has been doing, for quite some time now, and they are crystallizing in a point where it's ready to be shared with the world and made use of.
Yeah, for context, so Brendan Willard is among the people spearheading the V4 efforts, also the Aesara rewrite from Fiano, and he was, of course, in the show. I'm not sure I remember the exact episode number, but that should be something like 30. So if you're interested in these kind of computational symbolic computation and graph rewrites and so on, definitely check out this episode. Like, Brendan basically lays out the vision that you are witnessing right now with V4 and the presentation we are talking about. I have a question here from someone that I think you may recognize, called Ben Vincent. I don't know who that person is. And he's asking if there is an equivalent to clip for truncation, or if it's just the well-known pm.bound.
Right. So the answer is there is not yet, because truncation requires a new kind of operator. There's no, let's say, there's no operator you can call on a random variable to get truncation, because what truncation requires, when we want to generate truncated samples, is basically resample until you get something inside the range that you want. There is not yet, there's going to be. And PM bound does not do this either. So we're going to, PM bound does something a bit different, but we're going to have truncated variables, proper truncated variables quite soon in PyMC 3. I think it will be one of the points I mentioned later. So yeah, not the same.
Exciting. Thanks for your question, Ben. And he also has some encouragement like that. Nice with censoring. So I hope you appreciate that, Ricardo. We also have a question from Larry, but it's about a slide previously. So I'll let you go through the end of that slide, and then maybe we'll come back to that. So next case.
Right. So this is the big one. So one big limitation of V3 is we couldn't do anything with loops. And there's, many know a lot of interesting models make use, conceptually make use of what would be, a loop. For instance, in hidden Markov models, they're just, going through let's say, different indexes or doing some kind of transformation at every step.
Mm.
And in PyMC3, we couldn't, the first step is we couldn't call PM normal inside a scan loop, right? Just because our distribution was a hack, basically. So now we can call a random variable inside a loop, and we can look at some loops and ask whether this, corresponds to a log prop that we can, make sense of. And there's a lot of models that follow this pattern. So the Markov models I mentioned, but also things like random walks or random walks based on moving averages, things like that are very easy to write to generate, random draws, and now are going to be equally easy to model and to make inference with.
Yeah, that does sound super enticing. I love that. Using a lot of time series models. I can't wait for that.
Another one that's a bit of a... Right. Another one that's something that I find very curious is the order statistics. What's the probability of the maximum of 3 variables?
Oh, okay. Oh, that's tricky. Yeah.
That's tricky, but it's doable. So we can play a bit with CDFs, and we can answer these kind of questions, and we'll be able to make inferences with this kind of stuff. So and this happens in some kind of models. You are working with extremes, or you are working with minimums or even median, right?
Yeah.
So we're going to be able to model basically orders.
I see.
Cum sums, cumulative sums. They are used to represent some kind of random walks, right? Gaussian random walk. You can, take random draws of it by just defining a lot of Gaussians with some mean and standard deviation, then just do a cumulative sum of them, and this represents a random walk behavior. And we will in the future, in the hopefully near future, we'll just also work with cum sums in APPL.
Yeah.
And again, it's the nice thing that once we have one working, we're going to have, all kinds of cum sums working, right? Any kind of initial point plus any kind of distribution for the updatings with any kind of parameters, right?
So that should make a whole bunch of time series models much easier to work with and sample from.
Yeah.
Okay.
Right. And mostly, so what we are offering here is much more freedom in what you can model. You won't have to think, you won't have to look into the PyMC3 API and ask, is this, can I do this? You're probably going to be able to write it down and say, do this, and we'll be able to. And Ben already anticipated the need for truncated variables. Yeah, they are really cool. They are used more often than censored variables, and we really want to implement them.
Yeah.
They will be coming soon.
So let me go back to Larry's question. So he was asking whether we could briefly go over the differences between Y and YRV from one of the slides. So let me try and find that slide. And I think that's here, right? And so he's asking whether it's the same difference between X and X value from a previous slide too. So you seem to have understood the question, which is great. So I'll let you answer.
Yes, it is. It's good to know someone is looking at the code. Yeah, right, it is. We are creating a value variable that we need to pass because that's one input of the log P, right? We have to ask where.
So this is YRV?
That's, no, YRV is the original one, and Y is the value variable, which I'm creating here by, I'm defining it. I could have said YRV.type, which is a shortcut that's easier to get with the right type. Yeah, I'm just saying it's a scalar that I will use as input.
Okay, thanks. Thanks, Ricardo. And I know from the comments that Larry is still here, and so he should have gotten your answer. So now let's get back to the flow of the presentation. I think now you're going to wrap it up, right? So basically, what you just saw is a preview of PyMC 3v4 and what you can do with the new spin-off project, Apple. And yeah, now I'll let you give you the floor again.
Right. So now we want to plug it in, and it's already in a point that's, we can already get some of these new features. So we're going to use this as the backend to generate the log prop graphs. There's already a PR going on by Kostub, which was one of our Google Summer of Code students, together with me. He's doing the hard work of going through our code base and basically making everything go through APPL. And yeah, so the first picture here is an idea. So the figure on the left is an idea that we don't have this yet, but how we will interface for the users with the backend, so that they can indeed create these arbitrary random variables. One idea we have right now is that we'll just have something like pm.var, to which you can just pass whatever graph represents a random variable, and that will be your variable in the model that we see on the left. So you can pass a clip based on the, with a normal base, or you can pass a scan loop. And obviously now we always try to make our library user-friendly. We'll also have the custom, for many of these derived random variables, we're going to have some custom classes that, probably going to have a PM censored, the same way you have a PM mixture.
Yeah.
In the backend, we're just going to do this magic. We're going to create this graph with a clip and ask APPL for it. So yeah, we think that probably going to do these two things: have a generic var that you can pass everything if you want, and obviously also have helper, for different situations. So censored, maybe some random walks, stuff like that.
That does sound super nice. Okay, so we go to the next slide, and I think we're almost done, right? If I see it right here, so I'll let you conclude, Ricardo.
Yeah, so we are done. We are, so this was a sneak peek of one aspect of V4 I'm really excited about. We are planning to release a beta version of PyMC 3 V4, so people can use it just from pimp install, because we really want to start getting feedback, start getting bug reports, start really pushing it forward. Right now, you can install it through cloning our repository.
Master branch.
Exactly. Main branch now.
True.
And and the Aesara, if you are interested in working with symbolic graphs, or interested in exploring these the new backends we are developing, like Numb and Jax, we welcome you to try it out, see how it looks. And the APPL, the one I was talking about today, it's also published and ready to be tested, and with new features coming at a very fast pace.
Yeah, and the slides are available at the URL you see on the screen. Of course, I will share all of that on Twitter for people who are not present during the presentation, and also this video is recorded and will be automatically uploaded to YouTube, to my YouTube channel. So Alexandre Andorra. I know it's hard for you to say in French, but that's my real name. I will of course share the link to that, and of course feel free to share that with all of your friends, colleagues, family. Share that for Christmas. Talk about it during Thanksgiving, etc. I'm sure it will make for really great debates. So I think we are done. I'm gonna stop my screen sharing and thank again Ricardo Vieira, for coming on the show. That was your first time on the show. Granted, a very special episode. Like live episodes are always a bit harder. I hope listeners still enjoyed that. And so, thank you again, everyone, for tuning in. Thanks, Ricardo. Thanks to to all the PyMC developers who are working a lot on V4. Michael Ostege, for instance, who was in learn-based stats in a learn-based stats episode. Also, he works a lot on that. All of you, thanks a lot, guys. And yeah, Ricardo, maybe you have a last word.
Right. Thank you also for listening. Thanks, Alex. It was great and really, really looking forward for people starting using V4, and we can work on it.
Yeah, let's make that beta release happen. That's also why we are in Lisbon for the PyMC Labs retreat. So let's make that happen. Hope people will tune in and use that. And again, thanks for coming. Thanks for tuning in. And I'm really happy because it's the first time I can say live that pun that I love, and which is PyM Cheers.